All right, so let's take a look at the first problem from chapter 1. And these problems hopefully you'll see as a review for the most part, but I will guide us through. Okay, the first part says, this is a graph, shows power consumption in September in San Francisco. P is measured in megawatts, T is measured in hours starting at midnight, so be careful. This 0 represents midnight. Okay, and it says, what was the power consumed at 6 a.m.? 6 a.m. would be right here at the 6, and you go up until you touch the graph, go straight to the left, and that is 500 megawatts. So we would put in 500. Then it says 3 p.m. 3 p.m. occurs at 3 hours after noon, so noon is right here at 12. 3 hours after that would be 1500. So there is 3 o'clock, so we go up to the curve where it touches, straight to the left, and that is in between 800 and 900, and they'll generally give you nice numbers for this stuff. So we'll call it 850. Okay, then it says, when was the power consumption the lowest? When they say lowest, they're meaning when is the y value the shortest, or the lowest y value in the graph. Well, if you look, that occurs right about here. And the options they give us are 2 p.m. Well, 2 p.m. is right here at 1400. Definitely not that one. Noon is right here at 12. Definitely not that one. 6 p.m. is at 1800. Definitely not that one. Midnight is right here. Now that one is kind of low, but it's not the lowest. So the last one is right here. It's a little, so I guess they wanted that part right there. It's right at 4 a.m. So we would select 4 a.m. When was it the highest? So same idea. When is the very highest point in the y value? I'd say it's about right there, which is at noon. So that one we would say noon. Okay, now it says, do these times seem reasonable? So if we look at this, in San Francisco, folks, so at midnight, you know, they're closing down for the night. By 3 a.m., they'll probably have all the power off in the house. So they're sleeping, waking up, turning on lights, getting ready for work, going to work, using computers at work, lots of power at work, get off work, go home, cook dinner, and settle down for bed. So very reasonable. So your power is going to kind of peak in the morning and then reach the highest midday and then taper off at night as you're powering down for the night. And we've got it perfectly, so that looks good. Okay, for problem 2, it's going to be the domain of a polynomial. And actually, this is a rational function, so it actually has a polynomial on top and a polynomial on bottom. And actually, let's just review that real quick. So if you have a rational function where you have some polynomial on top and some polynomial on the bottom, we say that q of x cannot equal 0. So you can never divide by 0. And you can always, if you forget this, just try it on your calculator, take any number you want, and hit divide by 0, and it will say error or domain error, or it will say undefined. So that would be undefined. So for the most part, we just have to set the bottom of the equation equal to 0 and solve for when x makes it 0. There's an added twist to this one, and that is we can also not have the square root of negative numbers. So if you have the nth root of, let's say, x, if n is even, x has to be bigger than, I'm going to put it bigger than or equal to 0. So it has to be 0 or a positive number. If n is odd, x can be all reals. So it can be anything. But in this problem, we have to be doubly careful because we have a radical in the denominator So normally, and it is even, so it's the fourth root. It's kind of hard to see there. It's the fourth root. So it is even, so we would restrict x to be bigger than or equal to 0, but because it's also in the denominator, we're going to also restrict it from equaling 0. So what we're going to have is, let me write it, h of x is equal to 1 over the fourth root of x squared minus 5x. Well, because it's in the denominator, we cannot let it equal 0. So we're going to say everything inside that square root symbol, x squared minus 5x, has to be strictly bigger than 0. So it can't be negative, and it can't equal 0, because if it equaled 0, a lot of students don't remember this, the fourth root of 0 is 0. So you would get, if you had h of 0 in here, if you plug 0 in, you would get 1 over 0, which is undefined. So we have to solve this now. To solve that, we're going to factor out an x and get x minus 5 has to be strictly greater than 0. And now what you do with this is you get 2 points of interest. The points of interest are the values of x that make that 0. So there's 2 of them. If x is 0, the whole thing is 0. And if x is positive 5, the whole thing is 0. And now what you have to do is, get rid of some of this, you have to form a number line. And we're going to plug in those 2 what we call points of interest. So I'm going to form a number line. And let's plug 0 right in the center. And then our other point of interest is 5. And now we have to pick numbers. 1 to the left of 0, 1 in between 0 and 5, and 1 bigger than 5. I'd pick negative 1, I'd pick positive 1, and I'd pick 6. And we have to plug those 3 blue numbers into this function and see if they give us a positive value out. So let's try negative 1. It'd be negative 1 times minus 1 minus 5, which would be equal to negative 1 times negative 6, which is equal to positive 6, which is bigger than 0. So this one is positive, and it's going to be positive for all from negative infinity all the way up until 0. Okay, now we pick 1. So 1 minus 5 will equal 1 times minus 4, which is minus 4, which is not bigger than 0. That's negative. So any number in between 0 and 5 are not going to work. Okay, now we plug in positive 6. 6 times 6 minus 5 will be 6 times 1, which is positive 6, which is bigger than 0. So you're going to end up positive numbers there all the way until infinity. So it's kind of difficult to write this, but I will. In interval notation, the answers for this problem are all the regions of the number line that make that positive. So we would write it as negative infinity up until 0, not including 0, unioned with starting at, let's see here, we're excluding 0 through 5, so then we're starting at 5 again and going to infinity. So that's what it's going to look like. Now it's a little tricky to type this in, so let's see if I can get it right. It's going to be negative, infinity will be under the symbols button, infinity, comma, up until 0, end the parentheses. Why does it do that? It does double parentheses here. Then we go to the union symbol, which should be under, let's see, relations. Under sets, go to union, and then we have, it picks up from 5 and goes to infinity. Positive infinity. And that should be it. Let's try it. And we've got it right. So that would be problem 2. Okay, let's take a look at 3. So this has the absolute value function in it. And we'll recall that the absolute value of a number, let's just try some numbers. If you have the absolute value of negative 9, it equals 9. What absolute value does is it just measures how many jumps you are from 0 on the number line. So if I have negative 9 over here, it just says how many jumps do I have to make to get back to 0, and I'd have to make 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'd be 9 jumps to get back to 0. The absolute value of 9 is the same thing. So I don't care about direction here. I'm just counting 1, 2, 3, 4, 5, 6, 7, 8, 9 jumps to make it back to 0. It's really the distance from a number to 0. Okay, so what we have in this problem is we have, let me use a different color than what they used. We have the function is called a piecewise function. The function changes depending on the x value. So it has double the absolute value if x is less than or equal to 1, and it's just 2 if x is bigger than 1. So what we can do here is just pick a few x values and then plug them into the proper function and see what value we get. So there's two values of the function. The function is either going to be double the absolute value, or the function is going to equal just the number 2. And so let's just make it easy on ourselves. Let's just pick 0, 1, and I guess 2 is fine. So if x is 0, I'm going to plug it into the top function. So only the top function will get the number because it only accepts x's that are less than 1. So this is going to equal 2 times the absolute value of 0, which is 2 times 0, which is 0. And then the next one will be 2 times the absolute value of 1, which is 2 times 1, which is 2. And then that's where this function stops. So if it's bigger than 1, I plug it into this function, which just makes it 2. So if we look at this, when x is 0, I get 0. When x is 1, I get 2. And every number bigger than 1 is going to be 2, 2, 2. So it's got to be this function here. Well, maybe not. Let's look at this one down here. This one says the same thing, so it could be this one. So unfortunately, since we only picked 3 dots, we need to pick more dots. Okay, so let's see what happens when we pick negative numbers. So if we have x, let's pick -1, -2, -3. Now these all have to go into this function because it's the only one that accepts numbers smaller than 1. But these absolute values are going to make all these numbers positive, so this is still 2 times 1, which is 2. This would be 2 times positive 2, which is 4. This would be 2 times positive 3, which is 6. So again, these absolute values, this absolute value of x will change all these negative x's into positive numbers, and then the 2 out front will just double each one. So we should have, when x is -1, we're up at 2. When x is -2, we're also up at 4, so we should be up here. So let's see, did something go wrong with this? Oh, this is because they've played with the domain a little bit. So they're saying if the absolute value of x is less than or equal to 1. Well, the interesting thing about that is the absolute value of x will be less than or equal to 1 only if it's -1. So what happens is these values of -2 and -3, these ones should not even be defined. Let's see here, -2. So oh, yes. So the absolute value of -2 is going to be +2, which actually goes into the second function, not the first. There we go. So any -2 and -3, these will all be 2 as well. So we had to be a little careful there. So really, these would not have existed up here. So we would have this f of x equals absolute value of x because the absolute value of -2 is really +2, but this function said that the function is equal to 2. I wrote that wrong. The function itself is equal to 2 if the absolute value of x is bigger than 1. So the absolute value of -2 is 2, that's bigger than 1, so the y value is 2. The absolute value of -3 is +3, which is bigger than 1, so the answer is 2. So we would get this bottom left curve here. So be careful. You don't a lot of times see where they make the x value the absolute value of x. Usually they make it just x less than a number or bigger than a number, so you got to be careful there. Okay, determine whether f is even, odd, or neither. If you have a graphic calculator, use it to check your answer visually. So maybe we'll start with that. No, I'll show you the long way. Why not? So to do this, f of x is even if you plug in negative x and you get the exact same function out. It is odd if you plug in negative x and you get the complete opposite of the function out. And then neither would be, you don't get either of those. So we plug in negative x for x, and we get, so I'm using this function here. So it's negative x squared over negative x to the fourth plus 4. And now we account for these squares. So negative x squared, if you have a positive power, let's actually write that. If you have negative x to the power p, if p is even, I don't want me to write that. Don't. P is even, the answer is x to the p. If p is odd, the answer is minus x to the p. So if you have an even power, basically a simpler thing is to just remember this. If you have a positive, if you have an even power, the negative goes away. So this will be x squared. And then down here, this is an even power again to the fourth. So the negative is going to go away. You're going to get x to the fourth plus 4. Now that is the exact same function as the original. So these are the same. But we plugged in negative x. So if they're the same after plugging in negative x, this is called an even function. So we're going to select even. Okay, now I am intending you to sometimes graph your work, and to do that, I'm going to recommend some free software called Desmos.com. So let's go to that. It's super easy to use. Graphing calculator. And so our function was x raised to the second divided by, let's see here, second divided by x raised to the fourth, and then it was plus 4. So that's the function, and the key to an even function is that it's symmetrical about the y-axis. So you can imagine if you had a mirror placed on this y-axis, the left side looks like a mirrored reflection of the right side and vice versa. Another way to think about it is if you folded this graph across the y-axis, then the right side would fit perfectly on top of the left side. So that's another feature of an even function, is that it should be symmetric about a vertical line. It doesn't always have to be the y-axis, but it can be any vertical line, so it would be considered an even function. Okay, so quick showing of that. Desmos can be very useful. I mean, you saw how quick that was. Okay, let's move on to problem 5. Okay, maybe the best way to do this is just to show you each answer, because that'll kind of remind us about what these words mean. So a power function is something raised to a power. So down here, 9 to the t would be a power function. So maybe we'll get down there in a minute. Let's start with the ones we have. So log is a logarithm. So this is base 9 logarithm. So this is a log function. Let me just type in these answers. Okay, 9 square root of x. This is a root function. It's a rational, it's a radical, excuse me, not a rational, it's a radical function. Okay, for h of x, we had talked about this. When you have a polynomial divided by a polynomial, that's called a rational function. Okay, when you have some letter raised to powers and numbers, and you don't have any division or square roots, this is called a polynomial. And the degree is the highest power of the polynomial. So this is called the degree 2 polynomial because of all the letters in it, the highest power of those letters is 2. Okay, and then this one I already mentioned, this is a power function, so it has a base raised to some variable. It's called power function. And then if you have things like sine and cosine or tangent or cotangent, this is called a trig function. Okay, so I think that's all the different ones we have there. Oh, I didn't like this one that I put in. Oh, yeah, this would be, technically this is exponential function. Did I get them all? Okay, yep, we got them all. All right, 6. Okay, in 6 we're gonna want to review our basic functions. So if I have y equals some number in front of x, that's our classic straight line pattern that goes through the origin. So of all these lines, it's kind of hard to see, but it's going to be g. So if you look at g, it's just a straight line that goes up like this through the origin, and in this case it has a slope of 5, so it goes 5 up, 1 to the right, 5 up, 1 to the right. Okay, now 5 to the x, now that's an interesting one. So if you have y, and I should have tried to match these colors up beforehand, if you have y equals 5 to the x, you get, let's just pick some x values, you get 5 to the minus 3, 5 to the minus 2, 5 to the minus 1, 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3. Okay, so our x values are negative 3, negative 2, 1, 0, 1, 2, and 3. 5 to the minus 3 is 1 over 125, a really small number but not 0. 5 to the minus 2 is 1 over 25, small number not equal to 0. 5 to the minus 1 is 1 over 5, anything to the 0 is 1, anything to the 1 is itself, 5 squared is 25, and 5 to the third is 125. Now you will see a pattern here, negative 3 and positive 3 are reciprocals, negative 2 and positive 2 are reciprocals, negative 1 and positive 1 are reciprocals. And the way this shows up on the graph is it will be very, very small when x is negative. It will go through 1 when x is 0, and then it will climb very quickly. So if you look, and I actually got the color right just by happenstance, it is the blue line, it is f. Okay, now x to the 5th. Let me clear out these other ones. X to the 5th, let me see if I can get the color right just by looking. I believe it's going to be g. Okay, so x to, actually no, it's going to be probably red. Okay, so x to the 5th, once again we can pick negative values, so negative 3 to the 5th, negative 2 to the 5th, negative 1 to the 5th, 0 to the 5th, 1 to the 5th, 2 to the 5th, 3 to the 5th. And I don't have these numbers memorized, so I got to quickly do this. Negative 3 to the 5th is negative 243. The minus sign sticks around because the power is odd. Minus 2 to the 5th, I believe that's 32, but let me check. Yep, 32. So this is negative 32. Negative 1 to the 5th is negative 1. Anything to the 0 to any power is 0. 1 to any power is itself. 2 to the 5th is 32. 3 to the 5th is positive 243. So you notice that these are the same numbers but opposite sign. And so what we get is a curve like f where it's negative when x is negative. 0 is 0, and then it climbs very quickly like this. So we're going to have, this one is f, capital F. Okay, then the 5th root of x, very similar. It's going to look like, I'm just going to give this one away. If you plug in x's and y's, you will get a graph. Because it's an odd root, you can have negative numbers, and they will be negative, and then 0, 0, and then positive numbers will be positive, and so it's going to look like, looks like this black curve, lowercase g. Okay, and we got all those correct, and that's problem 6.